Okay, so I was asked many questions over the break, and I didn't even have time to answer all of them. And all of them are good questions. This is an intriguing definition. Okay, it's challenging, and those questions are going to be resolved gradually. Okay, it takes time to get used to and to sort out all the mysteries that can happen here, and we're going to do it gradually. So, for example, one question I was asked: if the function is not defined at the point A, so there's a hole here, how do we know what L is? How do we make that guess and then prove it? Okay, for example, that's a good question. Okay, so the answer is we're going to see examples. I can't give you all the examples right away. We're going to see them gradually. So, for example, we're going to see, so example 3 if you want, but I'm not going to prove it now. We're going to see it later. We're going to see that if you take the function sine x divided by x, this thing is not defined at 0. Do you agree? This is not defined at 0. But we're going to see that the limit of this function as x approaches 0, this limit is going to be 1. It's going to exist, and it's going to be equal to 1. Okay? The picture to go along with this thing, the graph of this sine x over x function, and again, you can only believe me now because I'm not going to do the details now. They're going to show up later. The picture to go along, the way this function looks, is something like, small picture. So there's a big hole here at 1, at 0. It's not defined at 0, but the function looks something like this. Kind of like a sine wave that gets mushier and mushier as you go out to infinity, and at 0 it approaches 1. Okay, this is the function sine x over x. We'll see this, we'll discuss this, we'll prove this, and in particular, it's not defined at 0, but it has a limit at 0, and that limit is 1. Okay? Clear? And we'll do many examples of various sorts of not having a limit, of limits where the value of the function at the point doesn't exist, and all kinds of things. We'll do those, but you just need to be patient. This is going to take time. Okay? Okay. So we know the definition now. We have the definition. What I want to do is start proving one by one elementary properties, elementary theorems, and we're building a machine. Gradually, we're going to have a big machine that will allow us to calculate limits and work with them more easily than seeking that delta for every epsilon in every example. That's not something you want to do. Okay, it's just too hard, too tedious. So here's our first theorem. If the limit of f of x as x approaches a equals L, so if in particular, or let's write if exists, if the limit of f of x as x approaches a exists, okay, then L is unique. A function cannot approach two values simultaneously. The limit is unique. Okay? That should make sense from the drawing. Okay? But how do we prove something like this? Okay? How do we prove? So what do we want to show? We want to show that it cannot be that there are two of them, let alone more. So we want to show that there can't be an L and a K, two different values, both satisfying simultaneously the definition of the limit. Right? So here's the idea of the proof. Proof. Assume that, so I'm going to prove this by contradiction. We've seen already proof like that, right? I'm going to assume that there are two. Assume that L and K one I'm going to take to be bigger than the other. Let's say k is the bigger and L is the smaller. Assume that L and k are both limits. If I get from this to some form of contradiction, that will prove that there can only be one limit. Okay? Yes?
But the contradiction is like for two. Don't you have to show that there are infinite and there can be
If I show that if there are two, I get a contradiction, that proves that
Then does it mean that there can't be two?
there can't be two.
But couldn't there be three?
Well, if there are three, in particular there are two. Suppose you have three limits.
Yeah.
Take any two of them, you get a contradiction. Okay? So if I show that there cannot be two, that shows that there cannot be more than one. Do you agree?
Yeah.
Okay.
So L is less than 3?
I have to decide, call one of them the bigger and one of them the smaller, so I just chose like this. Doesn't matter. So here's the picture. Here's what I'm thinking. Here's the intuition that's going on in my mind. I won't even draw the function, because I don't know what the function is. I'll just draw what's happening on the y-axis. That's where L and k live, right? L and k live on the y-axis. Do you agree? So I said that k is the bigger. Let's make a bigger y-axis. So let's say that this is k and this is L. Two values on the y-axis. Saying that L is the limit means that if I choose an epsilon, here's an epsilon neighborhood of L. By choosing a sufficiently small delta, I can guarantee that x's close, delta close to A, all have values landing here. Do you agree? That's what the definition of a limit says. Do you agree? But if k is also the limit, maybe just to make things more visible, let me take a bit smaller epsilon here. So this is going to be L plus epsilon, and this is L minus epsilon, and we know that I can guarantee by a small enough delta that all the f's land between L minus epsilon and L plus epsilon in a neighborhood of A. Do you agree?
Yeah.
But if k is also a limit, then I can take the same small epsilon and form an epsilon neighborhood of k, k plus epsilon, k minus epsilon, and x's close enough to A would have their f of x's living here. Right? But that's a contradiction. If x is close enough to A, since L is the limit, f of x has to be here. Since k is a limit, f of x has to be here. It can't be here and here simultaneously. Do you agree? Does everybody understand the intuition? That's the intuition of the proof. Yes? Now I have to formalize it. And proving a theorem in mathematics usually involves two steps, both of which are not trivial. One, getting the idea. That sometimes takes brilliance, and there have been brilliant people in this subject. Okay? In this case, it doesn't take brilliance. It's just really applying the definition. And the second step is spelling that idea out in a rigorous, accurate, mathematical way. And that's not easy either, at least not for starters. Okay? For beginners. So let's write it carefully. So assume that there are both limits. Define. I need an epsilon small enough so that these epsilon neighborhoods don't intersect. If I take a huge epsilon, then an epsilon neighborhood of k and an epsilon neighborhood of L would have a huge intersection, and f can be simultaneously in both, and there's going to be no contradiction. Do you see that? So I need epsilon to be small enough such that these two neighborhoods are what's called disjoint. Do you know that terminology? Disjoint neighborhoods. They don't have an intersection. Okay? So, for example, I could take the distance between L and K and divide it by 3. Okay? So define epsilon to be K minus L over 3. This guarantees that L plus epsilon is strictly less than K minus epsilon. That these two epsilon neighborhoods are apart. Okay? By the definition of the limit, that what?
That if you do K minus L over 3, then it's disjoint. Is that a theorem? Or did you just make it up?
No, I mean, it's a fact, okay? It's easy and straightforward enough that I wouldn't call it a theorem. That would be giving it too much respect, okay? If you don't see it easily, you can try proving it. What do you need to prove? So maybe I'll write here, up here, show that L plus K minus L over 3 is strictly less than K minus L over 3. So here's your little tiny practice homework. It's really a line, one-line proof. And that proves that these two neighborhoods are disjoint. Okay? So if you want to be completely rigorous, then maybe, yeah, you have to add in this tiny proof there. I think from the picture it's entirely evident and you can agree, but if you want to show it algebraically, go ahead. Yes?
No, I mean, it doesn't matter if you write 3, 4, 5, or 6. Just
Right.
It just needs to be greater than 2.
Right. Question? Okay, good. By the definition of the limit, there exists delta 1, let's call it. There's a delta for the L and a delta for the K. So there's a delta 1 such that if x is between a plus delta 1 and a minus delta 1, then f of x is between L plus epsilon and L minus epsilon. This is saying that L is a limit. I defined an epsilon, whatever it was. There exists a delta such that this holds. Do you agree?
We're saying this.
I'm saying that this follows from the definition of the limit. And this time, I'm doing something different than what I did in the examples of proving limits. In those examples, I had to prove that the definition of the limit holds. Here, I'm told that the definition of the limit holds, and I'm using that fact. Do you see that it's a different thing I'm doing? Likewise, there exists a delta 2 such that if x is between a minus delta 2 and a plus delta 2, then f of x is between k plus epsilon and k minus epsilon. This is from saying that k is a limit. This is from saying that L is a limit. Okay? Therefore, if I take, therefore, this implies that if x satisfies both, and there are x's that satisfy both, because these are both neighborhoods of A, right? So if x, so here's A, here's A, there's a delta 1 neighborhood and a delta 2 neighborhood. I don't know which is bigger, but take x, which is in both, that satisfies both this and this. It's going to satisfy both this and this, right? So it's going to be both here, not x. F of x is going to satisfy both this and this. So it's going to be both here and here, but that's a contradiction. So if x satisfies both, let's call it 1 and 2, if x satisfies both, then f of x, on the one hand, it satisfies this, so it's less than L plus epsilon. From our construction, that's the little drill above, this is less than k minus epsilon, right? L plus epsilon is less than k minus epsilon. Look at the picture again, or at the little practice thing that you can show algebraically. But this is less than f of x by the second property. So f of x is less than itself, and this is a contradiction. Yes?
Can you also prove by saying that if that condition were to be true, then you have to have a function with two values of y for one value of x. So you have to be vertical someplace, which contradicts the definition of the function.
Well, okay, so what I showed is, the point is that when you prove something, each line has to follow from the other in a way that's non-disputable, in a way that's rock solid. Okay? So what you're saying, if I was to somehow satisfy this, then the function would have to have two values. Why? How do you argue that? Prove it. Okay? So that would, of course, be a contradiction, but why does it follow from any of the things that are written here? Okay? What does follow is that this follows, okay, and f of x and f of x, okay, so you're saying maybe f of x and f of x are two different things. Okay, that's one way. I understand what you mean. That's another way of thinking about it. But this is a symbol for something. This is the same something. It cannot be less than itself. That's my way of thinking of it. Either way, it's a contradiction. Okay, I understand. Yes?
I was just going to add, isn't the actual question kind of like, I don't think you have to prove that it would give you two different values of f of x, because isn't that what the question's asking? Like, isn't the question saying, like, why can there not be two values of f of x here? Because
right.
because
Okay.
there's nothing.
Okay. We're really yeah. We're kind of saying the same thing. We are really kind of saying the same things in different ways, but I think the idea is clear. Okay. Do you agree that the idea, let's go back to this board, the idea of this picture really says it all, on the one hand, and spelling it out, I mean, maybe in a couple weeks from now, you look back, you will look back at this, and it wouldn't look hard. But right now, I can remember when things like this looked very scary to me. Okay, it's scary at the beginning, because we're kind of collecting a lot of notation and symbols, and this definition, which in its own right is not trivial, and you have to get used to it, okay? Gradually. You gradually get used to it. It's not, it happens, okay? It just takes a bit of time. Yes?
This theorem is just true for functions, right? Like if we have, for example, a circle, then this would not be true.
We're only discussing functions in this course, okay? We're not discussing general curves at all, only functions. Okay. Okay, so let's write down another theorem. So this completes the proof. Let's write down another theorem. As we go along, I'm going to choose some of the theorems to prove, and some not, because there's no way we can prove everything. So I choose some of them that kind of throw in new ideas, and we're not going to do all the proofs, of course. Okay? So here's another theorem. For some of the theorems, I'm gonna kind of present the idea, just the idea part, without formalizing the proof. If the limit exists, if there exists a limit, f of x and x goes to a, if the limit exists, then f is bounded in a neighborhood of a. Let's think a minute why this is true, and in fact that's the idea of the proof. Okay? What does it mean that there exists a limit? Okay, we still have the drawing on the board. Let's go to the drawing a minute. What does it mean that there exists a limit, that this L guy is a limit? It means that for any epsilon, I can guarantee, I can find the neighborhood such that all the values of the function land in this epsilon neighborhood of L. Do you agree? That was the definition. So, take an epsilon, whatever epsilon you want. He wanted 1 before, so let's take that 1. Look at L plus 1 and L minus 1. I can find a neighborhood here that would guarantee all the values being between L plus 1 and L minus 1. That's it. The function is bounded between L plus 1 and L minus 1. Do you agree? How many people followed that reasoning? Raise your hand if you're good. Okay, 50%. Let's say it again and see if we can get the other 50%. Saying that, maybe we'll draw it again with a bit less blur of all those. Here's the function. Here's the point A. Here's L. Take an epsilon. Take an epsilon. Take the orange. Then take an epsilon. Here's an epsilon. Let's say L plus 1 and L minus 1. The limit exists. You can take any epsilon you want. You're using the definition of the limit. You know it holds. I can find the neighborhood which will guarantee that f of x would fall in here. That's the definition. Where is that neighborhood? For example, from here to here. So do you agree that all the x's here, any x here, satisfies that f of x any x here satisfies that f of x is here. That was the definition of a limit. Do you agree to that? Everybody? But there it is. Any x here, the function is bounded between L plus 1, upper bound, and L minus 1, lower bound. It's only a bound in a neighborhood of A. It doesn't say that the function is bounded everywhere. For example, the function can look like this, right? It doesn't say that the function is bounded everywhere. It just says that it's bounded in a neighborhood of A. So in this neighborhood, it's bounded between L plus 1 and L minus 1. Do you agree? Raise your hand now if you're convinced. Okay, good, good. So there's a little tiny point of delicacy here, that if the function is not defined at A, or it could be defined, making it not defined at A is even the easy case. We can make it at A have a value somewhere out here, just to be annoying. Okay? So if at A it's defined out here, it would still be bounded, but the bound will we'd have to raise the bound to include this value. Well, we could do that. Okay? So I'm not going to write the formal details, but just the picture, just the idea. If it has a limit, then it's bounded in a neighborhood. Not necessarily on the entire domain, but in a neighborhood. Good? Question? Yes.
Why are we saying f is bounded in a neighborhood of A as opposed to L?
We're saying, when we're saying f is bounded, we're saying on which domain is it bounded. F is bounded in a domain which is some neighborhood of A. It's going to be that whatever delta that corresponds to this L. The bounds are going to be related to L. But the domain on which is bounded, which is what it means to say f is bounded where, then we have to state in which domain is it bounded. Question?
What if there are some problems like in that domain, like I've seen asymptotes from strings over there?
Here?
Yeah.
Well, the definition of the limit is going to guarantee that, I mean, you're saying, what if this happens really close to A? If there exists a limit, the definition of the limit tells you you're going to be able to find a small enough neighborhood that would leave these problems out, that would force all the f of x's into here. That's the definition of a limit. That's what it guarantees you. Let's look at it again. Never a bad idea to look at it again and again. The definition of a limit says if there is a limit for any epsilon, in particular for epsilon equals 1, for example, you can find a delta. There exists a delta such that if x is between these two values, if x is in this delta neighborhood, if x is delta close to A, you're good. F of x is between these two. So whatever problems you say may happen in whatever picture, you're guaranteed, if there is a limit, that those problems are going to be outside that delta neighborhood. Good? Those are very, very good questions. Very good questions. Yes?
Looking from here, I can see there is a symmetry on the neighborhood of x and on the neighborhood of f of x.
Right. We discussed that. We mentioned that this symmetry is kind of forced into the drawing I did before. And if it happens that when you do the drawing, you don't get a symmetric neighborhood, just make it smaller so that it does become symmetric. Okay? So the definition says there exists a symmetric neighborhood. We discussed it, okay? If you want, I can repeat it again afterwards. Okay? Okay. Okay. I'm debating whether to start the next theorem now or... Okay, maybe I'll just state it and we'll discuss it again next time. So, the next theorem is actually the first step towards that ultimate theorem that we mentioned, that for any elementary function, if it's defined at A, then its limit is going to be f of A. So this theorem is going to be the first step towards that statement. And the theorem is called limit arithmetics. And you'll see in a minute why this name. So, suppose f and g are both defined in... Remember, we used the terminology. I didn't use it yet, but I'm going to use it from now. a neighborhood of A that does not necessarily include A itself, we had a name for it. Remember the terminology we used? No? Right, punctured neighborhood. In a punctured neighborhood of A. Meaning a neighborhood of A may be excluding A itself. We don't care about the value at A itself. So suppose these are two functions defined in this neighborhood, and they both have limits. The limit of f of x as x approaches A is, which is L, and the limit of g of x as x approaches A is K. Then there are going to be four statements. One, if you take any constant times f, the limit of that as x approaches A is c times L. 2, if you add f and g, what is going to be the limit of the sum? The limit of the sum is going to be what? The sum of the limits, exactly. L, y, m, L plus k. The limit of the sum is the sum of the limits. The limit of a constant multiple is the constant multiple times the limit. The limit of a product is going to be what? Note that I'm using the other notation. Remember we had two notations? I'm using the other one now. Is what? The product of the limits, L times K. And the limit of a quotient, providing both limits exist, is going to be what? L over K. And here we have to put a restriction. What's the restriction?
K can be 0.
Right. K cannot be 0.
You also have to say g of x can be 0.
Right. You want to say also that g of x cannot be 0 because you're dividing by it, right? But that will follow from the fact that k is not 0.
Didn't we also say in the definition of the limit that it can't have to be greater than 0?
No, the limit can be 0. Right? The epsilon, right. The epsilon has to be greater than 0. L can be 0. There's no problem for a function tending to 0. Okay? But, yeah, here, I'm sorry, I'll add this. C is in R. C is some constant. Okay? Here, let's go back to this a minute. Saying that k is not 0, if the limit is not 0, then the function cannot be 0 in a neighborhood of A. Okay? Because it has to, the values have to be closer and closer to k, so they cannot be 0 close to A. Okay? So the fact that g is not 0 follows from the fact that k is not 0, and we don't need to write that explicitly. You can add it, it will still be true. Okay? So this is called limit arithmetics. You can see why, right? The arithmetics that we know, sum, product, quotient, pass to the limits. Do you see that? But I should remark, and it's very important, these statements only hold if L and K exist. Okay? So only when you know that you have an L and a K, you can do these sort of arithmetics at the limits. Okay? Okay. Yeah, so maybe we will discuss a bit the proof of this theorem next time. Maybe we'll prove one of these statements. maybe, for example, 1 or 2. They're not easy. Proving using the definition of the limit. That's the only thing we have to work so far with. And proving these two, especially number 4, is already quite hard. Quite hard. Okay, especially if for people who just met epsilon. Okay, it's quite hard. Okay, so let's call it a day for today and go home and think about this definition. Read it again. Look at the picture again. Try to get familiar with it. Try to get friendly with it.